I want to make just 2 more videos on coupled oscillators. I know if you've been looking at my videos like, oh, he's crazy on coupled oscillators. But you kind of do get in a groove. It's like, I want to do more, I want to do this, I want to do that. So I'm doing a couple more things. This one, I want to look at weakly coupled oscillators. And I have a demo to start off with. I made a video demo. So let's look at that. And it's not quite the same as what we're doing, but it is the same. So switching over to the video. Here I have, it's actually pretty, I kind of like it. So let me make it a little bit smaller. I have 2 masses on strings, and there's a spring connecting between them. So this is a coupled oscillation. The motion of the 2 masses swings. They both have a frequency to the swinging, but there's also that spring in between them. Let's just play this. So what happens if I give one mass an initial oscillation but not the other one? I get the following. I should have started that at the right spot. So now I'm walking over. I didn't edit that. So the one on the left swinging, and then it causes the one on the right to swing because it stretches that spring, but then it stops. And then the oscillation switch backs from the right mass to the left mass. So it switches back and forth, and that's just really cool. And the key thing here is that the frequency of the coupled there's 2 normal modes, which I should show you. Remember, we always have 2 normal modes. Let me see if I can see these 2 normal modes. I think this is it. Here's normal mode 1. No, this is both the normal modes. So here's normal mode 1, where the 2 masses start apart and move towards each other. And that has a different frequency of oscillation because that spring's pulling them back together. And then the other one is when they swing together, which, let's skip together. Nope, I'm doing it right now. And then if they swing the same, then that spring never gets stretched. So it's a different frequency of oscillation. But they're very close because that spring is very, very weak compared to the restoring force in the pendulum. So we're going to do the same thing. And I was going to do the same thing, but I want to use my other model of my Python model right here. So instead of 2 masses swinging, I'm going to have the same problem I've looked at before, 2 masses with a weak spring in between them. And so let's go ahead and set up the math of this, review the process of finding the normal mode oscillations, and then find all the math, and then we're going to model it here. So it's going to be great. Okay, so here's the problem that we have. Mass, mass, equal masses. These 2 are equal spring constants, weak spring constant in the middle, displacement from the equilibrium position. So the 2 equations of motion, there's 2 forces on mass, this first mass. There's a spring over here and that spring, but this spring force depends on both of these positions, and then the opposite is true over here. There's a spring, and then that force depends on both positions. If you do a little bit of an algebra, you can get it in this format. Mass times acceleration of position 1, that's ma, is equal to some constant, constant times x1 plus a constant times x2. And then the same thing is over here, okay? But that has it b x1 and then minus k plus b. And I'm calling b that spring constant in the middle. So what we want to do is to assume a solution that looks like this. The vector x is equal to a1, a2, e to the minus I omega t. If I assume that is a solution, so I'm finding the normal modes where they have the same angular frequency, and this is a vector saying, well, one of them is a1 times this, and one of them is a2. We want to find that. If you do that, I can take the derivative, the second derivative, and I get x double dot is negative omega squared, a1, a2, e to the minus I omega t. And this is all in the video. I'll put a link down below. I'll go through this in more detail. So if I do that and divide both sides by the mass, then I can write these 2 equations as the following using this. And this is equal to negative omega squared x, which is kind of nice. So if I write that, I'm going to divide by the negative sign on both sides. I get omega squared x vector is going to be equal to, now I can write this as a matrix, because see, I'm multiplying this by x1, x2. So this is going to be, but I multiply it by a negative to get rid of that, and I divide it by the m. So this is k plus b over m minus b over m minus b over m, k plus b over m, and all of that multiplied by the vector x. And now we have what's called the eigenvalue problem, because this says what vector x, in particular what constants a1 and a2, that the exponentials canceled. They were both there, they canceled. What vector a1, a2, when I multiply it by this matrix, do I get the same vector back with the constant? And that's the eigenvalue problem. Well, it turns out that we have two normal modes. So the first one, let's put it over here, because I'm going to run out of room. So the first normal mode, and this is all the stuff I did before, I could say x is some constant c1 times the vector 1, 1, e to the minus I omega 1 t, where omega 1 is equal to the square root of k over m. So this is the normal mode where the two masses do this, and they don't stretch that middle spring at all. It's the same as what we saw with the pendulums. And that's what this means. x1 and x2 both have the same motion. Those are both 1s. And that's some just constant just to normalize the whole thing. The other solution we get is x equals some other constant c2, 1, negative 1, e to the minus I omega 2t, where omega 2 is equal to the square root of k plus 2b over m. And again, if you want to see how to get those, there's a couple ways to do it. It's not too terribly difficult. You don't even have to do it with the matrix. You can find these normal frequencies by just doing some creative adding. But that's what we have right there. Okay, so now what we want to do is to make the assumption that these two are very close frequencies. So if b is a very small spring constant, then omega 2 is very close to omega 1. And in fact, let's define omega 0 as omega 1 plus omega 2 over 2. If that's the case, then omega 1 could be omega 0 plus epsilon, some small value, and omega 2 is omega naught minus epsilon, that small value. So I can think of it as a base frequency, and then one of them is going to be a little bit higher, one's going to be a little bit lower. But if you see, if I add these two together, I get the epsilon naughts. The epsilons cancel. The omega naughts, I get 2 divided by 2. So I do get that. It does work. Okay, so that gives me the following equation of motion, because the nice thing about these normal modes is that any solution can be a linear combination of normal modes. So if I take this plus that, I could get a solution. And in fact, I get two solutions because there's two solutions for C1 and 2 for C2, because there's two variables, x1 and x2. So let's write this as x equals C1, 1, 1, e to the minus I omega 0 plus epsilon t, right, because that's omega 1, plus C2, 1 minus 1, e to the minus I omega 0 minus epsilon t. So that would be a solution. It's just a combination of those two. And again, this is x1 and x2. That's why it looks like a vector. Now, if I include e to the addition, this is e to the minus I omega t times e to the minus I epsilon t. They both have this omega zeros in both terms, so I can factor that out. So let me write this as x equals C1, 1, 1, e to the minus I epsilon t plus C2, 1 minus 1, e to the minus, no, this is going to be plus, right? Plus I epsilon t, because minus plus. And then I multiply that by e to the minus I omega 0 t. Now, I mean, I did this before, but I need to find these constants. They're kind of arbitrary. Let's pick the case where C1 is equal to C2, which is some constant, the amplitude A over 2. So I'm going to pick that. I'm going to pick these two as the same. You can find C1 and C2 based on the initial conditions of x at t equals 0, x1 at t equals 0, x2 at t equals 0, x1 dot at t equals 0, x2 dot at t equals 0. And so you can pick out what you need to have. And we're just going to use a simple case like this. So we're going to use that. And if that's the case, then I can write these as two equations, right? I can do one for x1, because this is a vector, and one for x2. So that gives me the following. x1 as a function of time is a over 2 e to the minus I epsilon t plus e to the I epsilon t e to the minus I omega 0 t. And then I can do the same thing over here. x2 is a over 2 e to the minus I epsilon t minus e to the I epsilon t e to the minus I omega naught t. Now, these are complex numbers, right? So how do I deal with these complex numbers, because the solution's real, the things actually move? Well, I'm just going to take the real part of the solution. So to do that, it's going to be helpful to switch these back over to sines and cosines. I can use the Euler equation, which says this: e to the I theta is equal to cosine theta plus I sine theta. And then if you do the same thing, e to the minus I theta, if I put in negative theta, cosine of negative theta is the same as cosine of theta. So this is just going to be cosine theta minus I sine theta. So we got a bunch of trig stuff to do. Let's go up here with x1. x1 is going to be a over 2. This is going to be e to the negative I epsilon t, which is going to be equal to cosine epsilon t plus a over 2 I sine, minus is minus. Is that right? Yeah. Sine epsilon t. And then I have this term, a over 2 cosine epsilon t plus a over 2 I sine epsilon t. And then all of that is multiplied by e to the minus I omega naught t. And you'll notice, right, what happens here is I have these two terms cancel, these two add together. So I get a over 2 cosine epsilon t. And then this, let's write that as e to the minus I omega naught t is going to be equal to cosine omega naught t minus I sine omega naught t. But we only care about the real part, so we just get that. So then that's an epsilon. So I get that. And then cosine omega naught t. Oh, the 2's canceled. I had 2 of them. Now, if I do the same thing for x2, I don't want to write it out. But the only difference here is I have this is minus, right? So this is the same, and this is going to be minus. Is that right? I should get sine. Yeah, but then I get multiplied by a minus sign. So I should get a sine epsilon t. And then I still get the same thing over here, cosine omega naught t. I hope that's not cheating, right, to do that. So there I go. So this says, let's imagine that x1 at t equals 0. At t equals 0, this is going to have a position of a cosine epsilon, some small amount, and then this is going to be 1. This one's going to be 0, right? So at t equals 0, x1 is going to be equal to something. Let's just put something. No, it's going to be 1. Cosine of 0 is 1. Cosine of 0 is 1, right? So this is going to be a. And x2 is 0. But then as time goes on, this term's going to go to 0, and that term's going to go to 1. So I will get this stopping, right, because it's going to be multiplied by 0, and that one's going to oscillate. Okay, let's actually do this. So an epsilon, did we ever find what epsilon was? epsilon should be this, something like that. Well, what would epsilon be? Do we have a value for epsilon? Oh, it's just half the difference between the two frequencies. So epsilon is going to be omega 1 plus omega 2 over 2. So I know what that is. Okay, I can figure that out. Okay, let's go and do two things. Number one, I'm going to go to my Python model, and I'm going to just put a low value for the spring constant in the middle and give x1 a position, and let's just see if it reproduces what we expect, and then we'll plot this and see if we get that to work. We'll calculate epsilon. Okay, so back to the computer. Here we are in our computer code. Make it bigger. I've already have all this code. I'm not going to go over the whole thing. What I do want to change, K1, K2. Oh, I had different ones. K3 is 0, so I need to put that at 10, and then put this at, let's say, 0.5. Let's just see what happens if I run it. Okay, so that is one of the normal modes. It seems like it's okay. Now I want to go down here. I have x1 is 0.2, x2 is, some other value. Let's just put this at 0. And I apologize for the noise. I don't know what they're doing. I don't want to stop. Okay, so there's the one starts oscillating. And let's see if it stops. Let's see, look at the graph. I think it is. I think it's going to do it. I think when I want to make it oscillate a little bit higher frequency, I think that will help. So let's change this to 20 and that one to 20 and run it. Okay. I'm looking for the blue mass to stop. It doesn't look like it's stopping. Okay. Let's mass 1, mass 2. Let's make this a little bit smaller. Maybe that'll help. And then let's run this for a longer time. So 10 seconds. And let's run it at double speed because we're impatient. Yeah, okay, it did it. The problem is that the frequency that it shifts back and forth is epsilon. But you see here with this graph, we get exactly what we want. Let's increase that value of epsilon, and I think that will, B. I made B too small. That was my problem. So let's make B 1. Let's make it 2. Okay, there you go. That's pretty good. You can see it right here in the graph. Stopped moving. Stopped. That's perfect. Perfect. Okay, so what I want to do now is to just make another plot, add another plot here with my equations for epsilon. I'm going to do it for mass 1. So that's going to be this bottom mass down here. And I'll shift it up a little bit here so we can see it. I'll put it in purple. So let's go up here. No, let's make another graph. Let's call it F3. G curve, color equals color dot purple. And I need to find epsilon. So I don't have omega 1 or omega 2. That's fine. So we're going to put down here, I had another one. Omega 1 is square root of k over m. K1 over m1. They're the same. And then omega 2 is the square root of k1 plus 2 times k2 over m1. And then epsilon, I'll call it EP, is omega 1 plus omega 2 over 2. And then what would omega 0 be? I think it'd just be omega 1. It's close enough. Let's just use, I said omega 0 is equal to omega 1. I did say this. Oh, the difference. Okay, this is omega 1 plus omega 2 over 2. And this is the difference. And is that a positive or negative frequency? Omega 1 should be smaller. So let's put this backwards. Okay. Now, let's just go ahead and plot this thing. Let's calculate it. So I'm going to call it xcalc. And put it right down here. X1c is going to be equal to A, where A is the same value. What do they have up here? 0.02. So let's put that as 0.02. That's A1. That's fine. A1 times cosine epsilon times t times cosine omega 0 times t. Now I'm going to add on there plus 0.01. This will be shifted up a little bit and we can see it. And then I'm going to plot that. F3 dot plot T x3, x1c. I don't know if it's going to work. It might not work. See? Omega 2, I missed a parenthesis. Line 34. Omega 2 is the square root of, K1 plus 2K2, divided by. Okay, there's my two graphs right there, and they match up perfectly. That's a win right there. Coupled oscillators for the win. So, like I said, let me just tell you, the one more coupled oscillator problem I'm going to do is the double pendulum. The double pendulum normal mode for the double pendulum. I think it'll be pretty fun. So if you have any questions, or if I don't include all the links to all the different videos down below, let me know. I'll be sure to add them in there. And that's that.